Good morning, guys. Good morning, and welcome to our new webinar today. Speaking to you as usual, it's Omar, the application engineer at Radiocrafts. I wish we were speaking in better circumstances, but um, let's just hope everything turns out well and everyone lives in peace and happiness, though that's a bit hard, but that's what we always wish for. Good morning, Manye. And good morning, everyone. I see people are joining now one by one. Can give you a minute. You can, of course, feel free to introduce yourself in the chat window. You can grab a cup of coffee. You can get prepared because today we have quite an interesting topic and one which we haven't really discussed in a webinar before. So I really hope you get the most out of it. I had much fun preparing this because I think it's a fun topic, and it's maybe one which is better discussed and explained by voice. It needs this kind of interactive storytelling. So I hope you enjoy it as much as I did. And probably, as you can hear from my voice, I'm recovering from COVID. So if I sound a bit funny, that's just the virus effect. And if I mute for a second, I'm just maybe blowing my nose or something. So don't be alarmed, I'll not leave you. I'm here. Okay, so I see most people have joined by now. All right, so let's start. Okay, so the topic we're going to discuss today is actually how to connect RIIM to the internet. There are some common questions sometimes asked when discussing this topic. For example, how can I connect RIIM to the famous cloud services like AWS and Azure? Why do we have an example only for Things board till now? How does the differences between IP version 4 and version 6, how do these differences affect my connectivity options? What's a NAT table, static, dynamic, all these kind of questions. So we thought we can discuss this more with you today. All right, so as I said, my name is Omar. I'm the application engineer at Radiocrafts. We're going to speak today in this webinar for around 30 minutes. Try to keep it short. We will keep at the end 10 to 15 minutes to answer any questions you might have. So while I'm speaking, if you happen to think of any question, please write it down in the chat window you can see on your screen. And we'll do our best to answer all questions right after the presentation is done. And as usual, this is a recorded webinar, and the recorded version will be available very soon on our website in case you want to check it out again afterwards. Okay, so today we're going to speak about some points, as we said. We're going to first briefly speak about the internet in general. And then we're going to speak about how the internet works for RIIM and what differences there are. The, the topic for IP versions 4 and 6 and the differences between static and dynamic NAT and what is NAT and how does that affect you. And of course, our star slip, what it is and how is it used. And at the end, we're going to speak about how to connect to the famous cloud service providers. All right, so let's go. Oh, let's get back. Yeah. Okay. So why are we having this conversation in the first place? If any of you have seen a RIIM border router board before, you would know that it has an Ethernet port. So why can't we just plug an Ethernet cable into this port and connect to the internet? Well, life is never that simple. The internet is a complex web consisting of so many different kinds of hardware, protocols, communicating nodes. So entering into this intertwined web and exchanging data requires some adjustments and tweaks. So this is the internet briefly. In general, as you can see, many nodes, routers, switches, servers. So it's basically many kinds of hardware. And on this hardware, there are some protocols running. These protocols, they tell the hardware how to interact and speak with each other. Famous types of protocols are, for example, the hypertext transfer protocol, HTTP, and which is the protocol used to view websites through a web browser. You also have another set of two very famous protocols, TCP and IP, which is pronounced TCP over IP. And very briefly, they lay down some common rules and languages for computers and internet to speak with each other. So IP version 4 is the fourth version of IP. It uses 32-bit long addresses. But of course, due to the limitation that these addresses can run out and the number of nodes can be more than addresses available. So now we also have IP version 6, which is longer and can cover all the projected very high number of nodes projected for the future. And in general, we can say that the client always initiates communication to a requested server, like a web page, for example. So that's how the internet that you use every day, like when you want to visit a web page, your PC, here would be the client, would initiate communication to try to connect to the server hosting that web page. But in the internet that we use every day, no server can ever speak to you or communicate with your PC by itself without you initiating that communication, because that then would be a big security issue. If any server around the world can just ping or communicate or send packets to your PC without you requesting it. And that's why we have firewalls. Firewalls on your local area network, they protect your PC from unwanted incoming packets. Packets which are not part of an already established session where you are already exchanging packets with a certain web server. So that's for the internet. But with RIIM, what happens is that if you have a network, you might actually want that the server you're using or the cloud, you might want it to start pulling a certain RIIM node without the RIIM node initiating it, because now we're speaking about a different type of internet, an internet which is more for devices and battery operated devices and small sensors and so on. So here things get a little bit different, and then the advantages which we have in the normal internet, such as firewalls, can become some kind of disadvantage in this new architecture we're discussing now. But in general, in RIIM, inside the RIIM network, we have IP version 6. So that's how the RIIM nodes communicate with each other, being an IP mesh network. And just like the TCP over IP in the normal internet, if we can call it really normal internet, now in RIIM we have UDP over IP. The main difference is that TCP over IP includes negotiations and handshakes and establishing sessions and exchanging packets in the session and keeping the session open. This can be suited for your PC, which has virtually unlimited power. But with RIIM, we don't have that. So we had to change that from TCP IP to UDP over IP. That's what we use with RIIM. This really doesn't require sessions to stay open during exchange of packets, which means it's more suited for low power operations or devices which are running on a limited battery. And then we have something called network address translation, which is NAT. So what does NAT actually do? Very briefly, it translates private IP addresses to public and vice versa. So it can allow, if you have a local network, it can allow these local devices in your local network to access the internet through translating their IP addresses. And we will know more about this right now. So this is the internet from the eyes of RIIM. You can see that you have on the left-hand side, you have some mesh routers. They speak with each other using IP version 6, as we discussed. And then you have the border router, which is the root of the network. Border router has a NAT table, basically 624, because it translates IP version 6 addresses to IP version 4. So it's called 624. And then after that, in general, you usually have a modem if you're speaking, for example, about the network in your office, and then you have the big wide web. So what does this NAT table actually do? NAT allows the local mesh nodes, you can see on the left, in a private network to join a public network with a global IP address. For this to happen, the IP version 6 addresses of the RIIM child nodes must be translated to IP version 4. That's why it's called NAT 624. And of course, the opposite also happens for incoming packets. From the right-hand side to the left, the opposite happens. This global IP address is then translated to the local IP version 6 address of each node. But of course, for the NAT to do this efficiently, to route packets, the NAT table also takes note of the local port number of the child node. Okay, but what does that actually mean, and why can't we see an example? Yes, let's do that. Okay, so this is example number 1. Here's, I think, where the fun starts. We have here a very basic architecture of how a dynamic NAT would work. So basically with NAT, we have 2 versions, static and dynamic NAT. Both are very simple, and both will explain them with examples, and we'll tell you how to use each one and when to use this and when to use that. So here first we have the dynamic NAT. As usual, on the left-hand side, we have the mesh routers, speaking with IP version 6. Then you have the border router. Here it's a bit bigger because we need to explain what's happening inside the NAT. Okay, so what happens, let's say that mesh router number 3, there on the left-hand side, the bottom, wants to speak with the server on the web. Let's just call it now that any entity on the web they want to speak to, we'll call it the server for simplicity. So what does the NAT table do? The NAT table, first of all, you can see the first entry on the left. It takes note of the IP version 6 address of the sender node, which is here mesh router number 3. And then, of course, this is just an example IP address. And then it translates that to the IP version 4 address, which is the global one, which the border router will use to communicate with the outside world, and a port number. So when this packet reaches the server on the right-hand side and on the web, it will receive it not with the IP address of the mesh router, no, but it will receive it actually with the translated IP version 4 address here in the NAT table on the right-hand side, and with this port number. So what the NAT table did was that it assigned that mesh router node, it assigned it a port number and an IP version 4 global IP address. And then the packet is routed to its destination. So all this is in the case of uplink. Okay, then what happens in the case of downlink? Now you can see the arrow is reverted. Now speaking about downlink, let's assume now that the server wants to send an acknowledgement back to the mesh router. Let's say, for example, they were speaking using CoAP, and now the server is required to send an acknowledgement back. The server side, it knows the IP version 4 address, which it received the packet with, and the port number. So it would route that to the border router. The border router will go check his NAT table. He will find that he assigned that port number to this node, and then he will, using that port number, route the packet to the correct node because he already registered it on the uplink that it has this port number. Now let's go back again to the uplink for 1 second. Yes. Okay, back to this uplink example. As we see here, the problem is that the mesh router had to start communication. What if the server wants to start the communication? Now the server does not know the mesh router IP address, and the border router did not yet register the port number and the IP address of that node. So this basically means that if you are using dynamic NAT, you have to initiate communication always from the child node, because the outside world here on the right hand side does not know how to communicate with your local nodes. So this was the uplink. This is the downlink we spoke about. That's a summary. So what are the pros of using this example one architecture called the dynamic NAT? The pros is that any child node can send directly to the cloud, and it can accept downlink acknowledgement messages, and it's quite simple because it doesn't really require anything from your side as a user. All this happens automatically in the border router, and you're not required to do anything as a user. But the main issue with that is that the server at the beginning initially has no idea what's the port number of the certain child node, so it cannot just initiate communication with a child node. It has to always be a response. And of course, another thing is that the server has to reply in time, because if like 30 minutes later or 10 minutes later, if the server wants to speak again to that node using that same old port number, it will be erased, because this dynamic NAT, it changes, and this kind of entry recorded in the NAT table is only valid for a certain time, I think around 5 minutes, which should be more than enough for the acknowledgement to be sent. For the acknowledgement to be sent, and any more time than that, this entry will be erased, and that port number will not be valid anymore. And of course, this is just an example port number of what it can be. All right, so this was the dynamic NAT. I hope that was kind of simple. Now, the second flavor of NAT is static. Okay, what does that mean? Okay, this is made for the cases when you want to actually communicate from the server first. You want to initiate communication from the server side. Okay, how do we do that? In EC, using our APIs, you can actually print the network tree from the eyes of the border router. So what you will print is that the border router numbers all its child nodes. For example, it would tell you that this node is node 1, and then he puts this as 2, this is 3, this is 4, and it is actually kind of inform with the tree itself. The closest would have smaller numbers, and as you go further away, the numbers increase. So this would be 1, 2, 3, and this is more hops, so this is number 4, and so on. So you can print that kind of network tree with this numbering. And then you know that now, in using static NAT, things get different. The port numbers are different. Port number 10,000 is always the border router. Then you start counting from then, which means that in that network tree, any node which is node 1 would have the port number 10,001. Port 2, child node number 2 would be called, would have port number 10,002, 10,003, and so on. So you will have this list. So now you actually know from the beginning what are the port numbers. So this actually solves the problem of the dynamic NAT, in which we didn't know what port number the node has until it communicates first. But now, using static NAT, we know the port number even before the child node initiates communication, which is why it's called static, because they're kind of fixed numbers. So what you would do then, if you want the server side to communicate with the node first, you would just ask it to use those port numbers numbered as you saw it in the network tree. If you want to speak with the device which is number 3 in the network tree, you would know that it has port number 10,003. And that's what you tell it to use. And when it uses that, it will be routed through the static NAT table in the border router. It will know that this is 1003, and it will send it to that. And it is as simple as this. That's in the case of downlink. As we said, that static was made for this, to enable this downlink first kind of operation. All right, but what happens now, still in static, if that mesh node wants to send an acknowledgement back, like if you're using CoAP, which requires acknowledgements. Here, what will happen is that while the mesh router is sending the acknowledgement up to the server, it will go, of course, through the border router, but then it will be routed there using dynamic NAT. So actually, the server will not recognize that because it will be routed to it through dynamic NAT, which means that it will take this kind of port number, which is any number, not limited by this 10,000 numbering scheme. So this, of course, will mean that the server will not recognize what this packet is because it's coming from a different port number than the one it used to send. So how do we overcome this? There are many ways. First of all, we can use non-ACK CoAP, which does not require acknowledgement. So if you go up to the downlink, yes. So if the server side initiates communication using CoAP, which does not require acknowledgement, then the mesh router will not have to send an ACK and will not have to go through this dynamic thing and send it with a different port number and have the packet discarded and so on. So this is basically our recommendation if you want to use static NAT, NAT, yes, that you use no CoAP, no ACK CoAP messages. You might be asking which one is working by default in the border router, is static or dynamic? Well, as you can see, they are not either or. They are both there and they are both working by default. It depends. If you start communicating from a mesh node, like mesh node number 3, for example, if it starts sending up, then of course it will be routed using dynamic NAT, as we discussed in the first example. But if you go in EC using our API and you print the network tree and you get the device numbers, and then you use you say that the device number 3 is port number 10,003, then you ask the server side to initiate communication using that port number, then while coming down, the static NAT actually will be not enabled, but this is what will happen, and it will be routed down using static NAT. So this is so they are both working. It's not a mode that you can choose to enable this or that. Okay, so what are the pros and cons of this static NAT? Of course, the pros is that now we fixed the problem of always initiating from the mesh node. So now you can initiate from the server. And again, it's kind of simple because there's nothing special that you need to do except for this printing of a network tree, which is like one line of code. So it's not really complexity. The cons or the disadvantages of that is that the static NAT can only hold a certain number of entries. And actually, as you can probably by now predict, these port numbers 10,001 and 2 and 3, they depend on the mesh architecture, the network tree. Okay, what if for any reason you change the position of a mesh router or there is a new signal blocking, so the mesh has a new routing system or whatever happens? If any change happens to the mesh structure, it will of course mean that maybe a device which was number 4 to the border router would now become number 6 if the example now takes 2 more hops to reach it due to any change that you made yourself or due to any new wall being built or whatever. So this actually means that static, they're not so static, they can change if the mesh structure changes. So you always have to be aware of that and only use static NAT if you are sure that your nodes will not move, you'll not move them, and you will not build anything in your architecture which might change how the border router, the numbering sequence of how the border router sees the child nodes. And of course, it always depends on your firewall, because if your firewall is set with certain settings which can block any incoming packets, then the server will never be able to speak to your mesh node without your mesh node actually initiating the communication. So firewall might stop the incoming data. All right, so we discussed dynamic NAT. We discussed static NAT. So what do we actually recommend? We actually recommend this, SLIP. So what is Slip very briefly? Because I think we have more than one application note discussing this. We have GitHub examples, but very briefly, what Slip does is the following. So as usual, on the left-hand side, you have your mesh routers, your child nodes. Then you have a border router. Now forget NAT, because this NAT is only used if exiting border router is an Ethernet connection. But now we're not going to use the Ethernet connection, so we're not going to go through the NAT and all these stories. We will actually exit the border router through the UART interface. So Slip over UART, it keeps the IP version 6 packets. They are transferred over the UART interface to a Linux machine. This Linux machine can be a Raspberry Pi, for example, any single board computer which uses Linux. So Slip, it converts IP packets to be compatible for carrying over UART while maintaining its original IP core with just some small overhead. Now that Linux machine is set as a router, and the firmware you will run on this Linux machine to set it as a router and to accept these packets and to route them out and so on is provided by us. So on our GitHub, in our I want to say GitLab and GitHub, on our GitHub page, we provide that Slip example. I'm sure some of you are already familiar with that. You can just take that firmware and run it on your Raspberry Pi, and voila, it works. And of course, as a user, you are free to add any more implementation you want on your Linux machine. It's yours. You can do whatever you want, but we recommend, of course, using our firmware since it's what we developed and it has been tested extensively and it works. Then the Linux machine that will run that firmware, it outputs IP version 6, but now over Wi-Fi, Ethernet, over whatever. And here you can use any type of router, modem, or even cellular. Then you can reach the internet. So basically, what you have here is end-to-end IP version 6 without any network, without any address translation, without any more of these change in packets. So of course, the first advantage of using Slip is the end-to-end IP version 6. It means that you have the security of IP version 6 packets because packets are not opened in the middle anywhere in the architecture. Their packets are not opened and changed from V4 to V6 or so on. They stay IP version 6. And you can, of course, IP version 6 addresses are global, so you can address any node from anywhere. And you can initiate from the server or the child nodes or wherever you want. This basically global addressing. And maybe the only slight, if you can call it a disadvantage, is that you need here you need an additional node, which can be a Raspberry Pi, which I think all of us are familiar with, and they're not that complex to work with. So again, briefly, what Slip does is that we run a firmware on a Linux machine, which is provided by Radiocrafts. It takes the IP packets, which are sent over UART from the border router, not over Ethernet, but over UART from the border router, and it outputs them over Ethernet or Wi-Fi or whatever. So packets stay IPv6 all the way, and you get the security and you get the global addressing capabilities. Okay. So why did we as Radiocrafts have that example about connecting RIIM to ThingsBoard? Well, for us, that was the most simple because ThingsBoard Cloud actually supports CoAP. You can run CoAP resource there. So that made it very easy that we can just send from a CoAP resource to a CoAP resource, no matter using NAT or whatever, but it's CoAP to CoAP, so that was quite simple. And we have an application note about that, which you can check out from our website. And yeah. Well, the thing with the big names in the cloud services is that they don't really inherently support CoAP. So how do you connect RIIM to AWS cloud, for example? You can do this. So using Slip, again, this is maybe a third advantage to using Slip. which is that you have here Linux machine, which means you can run, for example, Node-RED, and then you can do whatever you want. So for example, you can use CoAP, but only send it to a CoAP resource on the Linux machine you're running. Let's say it is a Raspberry Pi. And then running Node-RED on the Raspberry Pi, you can take that CoAP from CoAP resource and convert or bridge the message from CoAP and make it MQTT. And of course, if you have MQTT, then you can speak with any of the big cloud services that we spoke about, because they do, of course, support MQTT. And how do you do this? We also provide this example on our GitHub page, how to bridge between CoAP and MQTT. So basically, you also have that option. If you want to use Amazon Cloud Services, for example, or Azure, you can always also do that. You will only need to send the CoAP only to your Raspberry Pi, and then there, using our firmware, our code, you can just convert CoAP to MQTT, and then you can speak with any cloud you would like. So I'm right on time, and just took 2 extra minutes of your time, but that's it. So what did we discuss now again? Very quickly, we spoke about different ways that RIIM can be connected to the internet. We spoke about dynamic NAT, where you can always initiate from the child node to the server. Then the server has to reply quickly with an acknowledgement, because entries into the dynamic NAT table are erased after 5 minutes. And you cannot really initiate from the server side, because the server side does not know what port number that child node is assigned. Then we discussed static NAT, where you can just print the network tree from the border router point of view, and then you can just use these numbers to know what port numbers they are assigned in static NAT, and then you can use these port numbers to initiate communication from the server side. Then we spoke about SLIP, which we recommend. It just takes the IP packets from using UART from the border router to a Raspberry Pi, and then there you can do whatever you want. You can route them out to the internet. You can use Node-RED. You can convert them to MQTT, then speak with any cloud service you would like, and so on. So these are the 3 ways. We ourselves, we recommend SLIP. It's the most simple. It gives you security of IP version 6 packets all the way, node source to destination, IP version 6. You have the global IP version 6 addressing. You have the Raspberry Pi, which is using Linux, which means that you can run anything on the Raspberry Pi, and you can basically have the freedom to adjust the operation however you like. We provide the firmware to download on the Raspberry Pi for SLIP, and we also provide the firmware how to bridge CoAP to MQTT. So guys, I hope you enjoyed this presentation. Hope you got something out of that and it was worth your time. Please feel free to write us if you have any questions in the chat window. We can have now a few minutes to answer if you guys have any questions regarding that. And don't worry if that was too much. It's recorded and it will be available on our website if you want to check it again later. All right, it seems that was pretty. Thanks, Peter. I really try to make it clear. You know, it's not very not simple topics we're discussing, so I try to make it as clear as possible. Don't worry if you don't get it all now. It took me much trials to wrap my head around that. So yeah, but I'm glad that you thought it was clear. And seems like it was clear for everyone. We don't have much questions, which is very good news for me. I feel like I did my job. Thank you, Niels. All right, guys. So hope you had fun. Hope this was worth your time. Feel free to check the video again later when it's posted on our website. And take care. And yeah, stay safe. Have a nice Thursday and weekend. Goodbye.